Okay, we're at 16.7, section 16.7, speed of sound waves, and we've got our little pressure tube that we've been working with, and you can see that the uh, uh, pressure times the area, that's the force, this is the volume here. The volume is going to equal the area times V delta T. Well, V delta T is your delta X. And so let's look at it from a momentum point of view. The change in momentum is equal to impulse. Well, what is impulse? Impulse is equal to the force times delta T. So the force is uh, a delta P times the delta T in the I direction. So delta P is equal to the bulk modulus uh, minus the times the negative Vx over A delta T times velocity A delta T is equal to BVx over V. So the impulse is equal to AB Vx over V delta T in the I direction. So the momentum is equal to the mass times delta V, which is PV initial times Vx in the I direction minus 0, which is equal to the density rho V Vx A delta T in the I direction. So PV Vx A delta T is equal to AB Vx over V delta T. So the same equation that gives you that V is equal to the bulk modulus divided by the density. Now, if you recall from our the velocity of a taut string, a stretched string, the velocity is equal to the tension divided by um, the mass density of the string. And so you have this, in general, you have the velocity is equal to the elastic property, the square root of the elastic property divided by the inertial property. And that simplifies if you recall on our previous set of slides, we ended with delta P max equals to BS max times K, where B is the bulk modulus, K is the wave number. And now the wave number is 2 pi over the lambda. Well, if you multiply top and bottom by the frequency, 2 pi f is equal to omega, and 2 pi, lambda times f is equal to the velocity. So we can, we just, we have that the b is equal to the, in other words, if you square both sides here, you have v squared is equal to b divided by the density. So b is equal to v squared times the density. We make that substitution here. Density times v squared for b times s max times the omega over v, the 2 pi over lambda multiplied by f top and bottom. And that gives you the density times the volume times omega, the angular frequency, times S max, which is a much simpler equation to derive than this one, because you don't always know the bulk modulus of of what you have, but you do have the density, and we have the densities right here for different media. You can see hydrogen is 1,286, helium 972, air about 343 at 20 degrees C. The 972 is much higher than the 343. That's why. And I'm not going to recommend this because you don't always know the purity of the helium that you get from a balloon, but you've seen videos of people inhaling the balloon and the helium from balloon, and their voice sounds much higher. Well, it's because the speed of sound in helium is much higher. Uh, and you can look at it in liquids. It's anywhere from 1,904 for glycerol down to 926 for carbon tetrachloride. All of them higher than the speed of sound in air. And then you can see in medium, in solids, they're all much higher than the speed of sound in air, with the highest being aluminum, 6,420, to the lowest being rubber, 1,600. Now we're going to learn that the velocity is temperature dependent, and the equation for the velocity of sound in air is 331 meters per second times the square root of 1 plus the uh, uh, temperature in Celsius divided by 273. 273 happens to be 0 degrees C. So as an example, in a room or if the air is 20 degrees, like room temperature, that's V is equal to 331 meters per second times the square root of 1 plus 20 divided by 273. That's approximately 343 meters per second. And we can use that fact. They show a picture of lightning, and when you see lightning strike, if you count up to three, since 333 meters per second would be a third of a kilometer. 333 meters is a third of a kilometer. 343 is approximately a third of a kilometer. So if you see a lightning strike and you start counting by three, if you hear it 3 seconds later, it's only a kilometer away. If you hear it 6 seconds later, it's 2 kilometers away. If you divide by 5, you get about, since the sound is 1,100 feet per second and a mile is 5,280 feet per mile. If you count by 5, that gives you about how many miles it is. So you divide by 3, you divide the number of every 3 seconds, you're a kilometer away from the lightning. Every 5 seconds, you're a mile away from the lightning. And I think that might be, yes, that's it for the speed of sound and temperature. Okay.